The beginnings of relativity. Most of our everyday experiences and observations have to do with objects that move at speeds much less than the speed of light. Newtonian mechanics was formulated to describe the motion of such objects, and its formalism is quite successful in describing a wide range of phenomena that occur at low speeds. It fails, however, when applied to objects having speeds approaching that of light. To study objects having speeds approaching that of light, we must use relativistic mechanics. Before starting, some physical concepts must be well defined. By the way, if you like this video, don't forget to like and subscribe to this channel and activate the bell. It's very important for the continuity of this channel. Reference frames. Let's start by revisiting a classic problem of the relativity of motion in physics to understand why the concept of a frame of reference is so important. If you say, for example, that you are traveling in a car with a speed of 100 km per hour, it means that your car is moving 100 km per hour when seen by another observer at rest on Earth. Suppose now there is another car in front of you with a speed of 80 km per hour when seen by the same observer at rest on Earth. An observer at rest on the road, that is, zero speed in relation to the ground, sees the two cars at 100 km per hour and at 80 km per hour, respectively. But when this situation is seen by the green car, you will be approaching it with a relative speed of 20 km per hour measured in the reference of the green car. All measurements must be made relative to some frame of reference when quoting a velocity of an object. It's very important to say what the velocity is measured relative to. A frame of reference is just something you use to measure the things that matter in physics problems, that is, positions and velocities. Based on this simple but very significant example, we conclude from the point of view of classical physics that all movement is relative, as it depends on the observer, that is, on the adopted frame of reference. Velocities measurements are always relative since velocities depend on the adopted frame of reference. Wave behavior and the relativity of motion. Before continuing, let's recall a bit about the properties of waves you've already studied. We must remember that waves carry energy, not matter. In other words, the energy propagates without dragging the medium. The speed of a wave does not depend on the speed of the emitting source. The first statement above is easily observable. When you throw a stone into a lake, you see circular waves moving away from the point where the stone fell, making the water ripple up and down. But the water particles are not dragged by the wave. The second statement requires a little more thought. Imagine a car that can emit beeps through the horn. The sound of the horn leaves the source with a speed of 340 meters per second in relation to the air. The speed of sound is measured in relation to the air, and therefore it does not depend on whether the car is at rest or moving in relation to the ground. If there is wind in the place, the speed of sound in relation to the ground changes because it's worth 340 meters per second in relation to air molecules. Let's go back to the car problem discussed at the beginning of this video. A car travels at a speed of 100 km per hour relative to the ground, and in front of it another car travels at a speed of 80 km per hour, also relative to the ground. Consider that there is no wind. As we have discussed, if any car touches the horn, the speed of sound will be 340 meters per second, or 1,224 kilometers per hour, measured in relation to the air. If the green car honks, the sound goes toward the car behind with a relative speed of 1,324 km per hour. The sound moves with a speed of 1,324 km per hour relative to the gray car. If the gray car honks, the sound goes towards the car ahead with a relative speed of 1,144 km per hour relative to the green car. By the end of the 19th century, wave movements were already well known. The light was interpreted as an electromagnetic wave. It was believed at the time that every wave, mechanical or electromagnetic, would require a medium to propagate, even though Maxwell's electromagnetic theory stated that the speed of light always has a fixed value in free space. They proposed that such a medium existed and gave it the name ether. The ether was assumed to be present everywhere, even in empty space, and light waves were viewed as ether oscillations. These concepts are indeed strange. Some physicists suspected that the ether idea was wrong. Among other things, if the ether existed, it should offer friction to the planet's motion. There would be friction to be overcome, and therefore the planets should slow down. However, there was no evidence that the planets were slowing down from being submerged in the ether over the years. We have two possibilities, that is, the ether exists or does not exist. If the ether exists and the observer moves relative to it, just as the observer can move relative to air, then we must add or subtract the speeds of light and the observer, just as we did with sound. Pay attention in the figure. If the ether does not exist, the speed of light is absolute and, therefore, its measurement will not depend on the observer. Pay attention in the figure again. An important experiment proposed by physicists Michelson and Morley in 1897 was intended to measure the Earth's relative motion in relation to the ether. If v is the speed of the ether relative to Earth, then the speed of light should have its maximum value, c plus v, when propagating downwind. Look at the figure. Likewise, the speed of light should have its minimum value, c minus v, when propagating upwind. Look at the figure. Even though the Michelson-Morley experiment was repeated at different times of the year when the ether wind was expected to change direction, the results were always the same. No fringe shift of the magnitude required was ever observed. In 1905, Albert Einstein rejected the idea of an ether that permeates all of space and suggested that light is an electromagnetic wave that requires no medium for its propagation. In fact, Einstein stated that the speed of light, like any other wave, is independent of the speed of the emitting source. The speed of light and electromagnetic waves, unlike mechanical waves, is absolute, that is, it's constant and independent of the observer as predicted in Maxwell's electromagnetic theory. This last statement reveals the peculiar behavior of light and electromagnetic waves, and, at first, seems to be just a curiosity. However, it has incredibly revolutionary consequences, as we will see in the next video. Thanks to the enormous popularity achieved by the theory of relativity, which we are beginning to analyze, it's very common to hear people saying that, according to Albert Einstein, everything is relative. Nonsense. This is not true, and it has never been said by Einstein or by any other physicist. According to Einstein, the speed of light is absolute. We know the speed of sound is not. See from this simple example that claiming that everything is relative is bullshit. It needs to be very clear that there are relative quantities, but there are also absolute ones. Generalizations in relation to the theory of relativity become relativism and not relativity. So, from now on, be very careful. Relativism makes knowledge subjective.